Hi everyone, this is Dr. K. Kannan, Assistant Professor, Department of ECE, R.M.K. College of Engineering and Technology. In this lecture video, I am going to continue my mode theory. So this mode theory deals with the propagation of light in optical fiber. So this topic coming under Unit 1 in the heading of Introduction to Optical Fiber. So here, look at the diagram. So this diagram says that the direction of wave propagation in the Z direction, and in this Z direction, it is in the axis of the fiber core, and how this will converted into cylindrical coordinate system we will see. So the cylindrical coordinate system used for analyzing the electromagnetic wave propagation in an optical fiber. Now look at that, in the left side you have the x-axis, y-axis and z-axis, and the z-axis which is aligned or which is there in the optical axis, optical fiber axis, that is converted into cylindrical coordinate system. In cylindrical coordinate system, we know that the basic parameters are r, pi and ez. R, it is a radius of the cylindrical structure, and pi, it is azimuth angle, and z represent the height of the cylinder. So we can represent x, y, z in terms of a triangle, rectangular coordinate system, where we finding one point P. So the point P, distance from the origin from x, y, z, it is r, pi and ez. Now consider the Maxwell's equation. Using cylindrical coordinate system, the electric field intensity E is equal to E naught of r comma pi e power j omega t minus beta z. So here E, it is electric field, and E naught, it is intensity, or we can call it as the magnitude of that wave E naught r comma pi e power j omega t minus beta z. Similarly, for magnetic field equation, the magnetic field intensity, it is h naught of r comma pi, that should be multiplied by e power j omega t minus beta z. So substituting these two equations, E and H in our general maximum curl equation, then we will get 1 by r of dou by dou pi of Ez plus jr beta e pi is equal to j minus j omega mu hr. So similarly, we can get the value of j omega mu h pi and minus j omega mu hez. So the equation 11, 12 and 13, it's related to magnetic field intensity with respect to the radial component and the azimuth angle and z direction. So all are in magnetic field equation. And in the left side, you have the equation in terms of electric field intensity. Okay, then similarly for the same method, we are going to find out the electric field intensity equation. Now look at that, the equation 14, 15 and 16 represents j omega mu epsilon mu er. So that is the electric field intensity with respect to railway direction, which is equal to 1 by r of dou by dou pi of hez plus jr beta h pi. Similarly for j omega mu e pi azimuth angle, j beta hr plus dou hez by dou r. Similarly for electric field component in z direction, it is minus j omega mu e z is equal to 1 by r of 1 dou by dou r of r h pi minus dou hr by dou pi. So by eliminating the variables, these above equation can be rewritten such that when Ex and Hz, that is electric field intensity in x direction, magnetic field intensity in z direction are known, the remaining transverse components are determined. From that equation, we can have the electric field intensity in the radial distance as well as the angle. Similarly, for magnetic field intensity at the radial distance and with azimuth angle. So ER, E pi, HR, H pi. So equation 17, 18, it is related to electric field intensity. 19 and 20 in the form of magnetic field intensity. Now we can substitute these ER, E pi, HR, H pi into general equation. We will have the final two equation in terms of electric and the magnetic field. So dou square E Z by dou R square plus 1 by R into dou E Z by dou R plus 1 by R square dou square E Z by dou pi square plus Q square E Z equal to 0. So this is the equation in terms of electric field intensity. Similarly, for the magnetic field intensity, it is dou square Hz by dou r square plus 1 by r dou Hz by dou r plus 1 by r square dou square Hz divided by dou pi square plus q square Hz. So equation 21 and 22 represents the electric field equation and the magnetic field equation. Okay, then the above two equations shows that the coupling between Ez and Hz is required by the boundary conditions. So if the boundary condition, if it is not lead to the coupling between field components, then the mode solution will such that Ez equal to 0, or we can have Hz equal to 0. That is, electric field intensity in the z direction is equal to 0, or otherwise the magnetic field intensity in the direction equal to 0. So when Ez equal to 0, then we can say that it is a transverse electric. Similarly, when Hz is 0, then it is called called transverse magnetic. So the hybrid mode exists if both are non-zero, or we can say that it's a degenerated mode of HE and EH. Then we go for the structure of the fiber. So consider the structure of the fiber is cylindrical fiber. Then the exact solution of Maxwell's equation for cylindrical dielectric waveguide it's very complicated, and that will give the complex result. So in a common with a planar waveguide, the TE TM modes are obtained within the dielectric cylinder. So cylindrical waveguide is bounded in two dimensions. Therefore, the two integers, that is L and M, we can specify using the modes, that is called TE-LM and TM-LM modes. Okay, then these modes are result from the meridional ray of propagation within the guide, that is within the optical fiber. So hybrid modes where both EZ and HEZ are non-zero, so result from skew ray propagation within the fiber. So this can be designated by HELM and EHLM. So LM, it's a suffix to represent the mode, depending upon whether the components of the electric field and the magnetic field make larger contribution to the transverse field. So then we are going to discuss about the modes in cylindrical fiber. So in the modes in cylindrical fiber, we are going to define based on the weakly guided approximation. So analysis is simplified by considering the fibers for communication purpose, where the guiding nature, that is the guiding nature approximation, where del is less than 1. So we know that del it is a profile, index of profile. If it is less than 1, that is small grazing angles, then that will approximate solution for the entire set of EH, HE, TE and TM modes may be given by two components called linearly polarized component. That is EH and HE modes pair occur with almost identical propagation constant. Sorry. So degenerate mode. So degenerate mode means the superposition of these degenerating modes characterized by a common propagation constant correspond to a particular linearly polarized mode regardless of the HE, EH, TE or TM configuration. So this linear combination of the degenerate modes produces here usually the simplification in the analysis of weakly guiding in nature. So weakly guiding means the del value is always less than 1. Then linearly polarized mode is called the weakly guiding nature. So instead of del, we can substitute n1 minus n2, the difference between core and cladding. So n1 minus n2 is less than 1. So these fields components are called linearly polarized mode and are labeled by LP, JM, where J and M designate mode solutions. So here these are all the basic wave equation to represent the modes for EH and HE modes. So when del is less than 1, we have the K1 square equal to K2 square equal to beta square. So K1, it is a propagation constant with respect to medium 1 and medium 2. So both are equal to beta square. So here JV plus KV is equal to plus or minus P by A of 1 by U square plus 1 by W square. So this equation that represents the value of the recurrence relations. So by using this one, we can get two set of equations: V1 of UF divided by U JV of UF plus KV1 V plus 1 omega A and WKV omega equal to 0. So the solution of the above equation that gives some set of modes is called EH mode. So EH mode and HE modes are, it is a hybrid mode. So accordingly, we can have the different values of the HE mode and EH modes in terms of K, that is K1 and K2, and in terms of beta square. So then we can represent the J value. So J value is equal to 1 means then it is called TE mode and TM mode. If J equal to V plus 1, then we can have EH modes. And if J equal to V minus 1, then we can have HE modes. So therefore, from the equations, we can return the form, that is U J suffix J minus I minus 1 of UA divided by J of UA, which is equal to minus of omega K J minus 1 of omega A divided by Kj of omega A. So this equation, that is J, and the next equation shows that within the weakly guiding approximations, all the modes are characterized by a common set of I and M that satisfies the same equations. So this is a representation of the linearly polarized mode. So here for the general thing, we have LP01, LP11 and LP21 modes. These are the linearly polarized mode. From LP01 we can get hybrid mode of HE11. Then the field distributions are parallel, right, parallel to the axis. So it is in only one direction. So the intensity is fully occupied by the electric field intensity with respect to x direction. Then when you go for LP11 mode, where we can have TE01, TM01 and HE21. So for T01, the field nature it is in the circular form, so that we have the intensity distribution is semicircle. So it is a semicircle, one off and another off. Then similarly for TM01, where the field distributed it is from the center to the core cladding interval, that is at the boundary. So we can have the split off by the vertical. So similarly for HE21 mode, where you can see the field distribution, right? It is a the flow of the field from the top to bottom to right to left. So like that we can have, but the intensity distribution is both are same for TM01 and HE21 modes. Then finally we have LP21 mode, where we have EH11 and HE31 modes. Then we can have the field distribution in the form of a star-like structure, and where the field intensity distribution also it is a different form. So this is a general representation of linearly polarity modes of LP01, LP11, LP21 and corresponding hybrid modes, and the field distribution with the intensity distribution of electric field intensity in x direction. Okay, then we can represent the linearly polarized mode by the values. So with the exact value, you can represent in terms of hybrid mode. Corresponding hybrid mode value in the linearly polarized mode is given. Okay, so correspondence between the lower order in linearly polarized modes and the traditional exact mode is given. For example, LP001 it is a linearly means, then corresponding exact one it is HE11. So similarly LP11, LP21, LP02, LP31, LP12, and finally it is LP So the LP in terms of linearly polarized mode, so exact mode means it is a combination of electric and magnetic field. So that we can call this one it is a hybrid mode. So then we can have leaky modes and guided modes. So here we are defining leaky mode and guided mode based on the beta value. So here look at that, the beta value it is in between N2K to N1K. So N2K less than beta less than N1K. So when beta equal to N2K, then we can say that mode is called a cutoff mode. Here the mode phase velocity is equal to the velocity of light in the cladding, and mode is no longer properly guided. Then we can say that mode is a cutoff condition. The next one unguided, or we can say that leaky modes, or we can say that radiation mode. So the frequency below the cutoff, when beta is less than into k, then it is called a radiation mode. That means all the power flow in the cladding. So the wave propagation does not is abruptly below cutoff. So mode exists near the core cladding interface. Okay, then we go for guided mode. So where the guided mode is beta is greater than N2K. So less power is propagated in the cladding until at beta equal to N1K. So all the power confined to the core. So this range of value of beta signifies guided modes in the optical fiber. Then we have mode overview. So the order of the mode is equal to number of field zero across the grid. So already we have seen this one. So here we have the leaky modes are only partially confined to the core region and attenuated by continuously radiating their power at the cladding. So we can have that power radiation out of the waveguide is called a tunnel effect. So the boundary between truly guided modes and leaky modes is defined by the cutoff condition B equal to N2K. Then we have mode coupling. So mode coupling means the power flow from one mode to another mode. So the power flow from one mode to another mode means there is a perturbation during the propagation inside the waveguide. So how it will be done, or how at what condition or what parameter we have to consider for mode coupling. So there is a deviation in the fiber axis from the straightener, and the second one variation in the core diameter. Then the irregularities at the core cladding interface. The next one, the refractive index variation changes the propagation characteristics of fiber. So have this effect of coupling energy traveling from one mode to another mode is called mode coupling, or we can have mixing. So this mode coupling will affect the performance of optical fiber communication. Then we have the concept of key model. So key model means the mode theory. So where we are going to talk about the important parameters called V number. So that is called normalized frequency. So V number can be used to express the number of modes capital M in a multimode fiber when V is large. So an estimate of the total number of modes supported in any fiber in general equation M equal to, that is not equal, it is approximately equal to 1 by 2 of 2 pi a by lambda whole square n1 square minus n2 square. So we can represent that one in terms of V. So M equal to or approximately equal to V square by 2. Then keyword concept, where V number we can define by V equal to 2 pi a by lambda into n1 square minus n2 square whole power of, where n1 square minus n2 square whole power of, it is a numerical aperture, determines how many modes a fiber can support. So except the lower order mode, that is the G11 mode, each mode can exist only for the value of b that exceeds certain limit of the value. So that exceeds certain limiting value. So the modes are a cutoff condition. That means when b equal to n to k. So this can occur when the range of b is less than or equal to 2.405. So where the higher order mode, that is He1 mode, has not cut off and chooses to exit only when the core diameter is 0. So when b number approaches cutoff for any particular mode, then more number of mode power, hybrid mode power is in the cladding. So then far from the cutoff or larger value of V, then the fraction of average optical power residing in the cladding can be represented by P clad by P. So capital P, it is a total power, and P clad, it is a power flowing through the cladding. So P cladding by P is equal to 4 by 3 of m power minus 1 by 2, where P, it is the total power of the for total optical power in the fiber. Since m is proportional to v square according to the formula, the power flow in the cladding decreases as v increases. So this increases the number of modes in the fiber, which is not desirable for a high bandwidth capability. So for step-index fiber, the fractional power flow in the core cladding is given by P clad by P approximately equal to 4 by 3 into root term, where m is proportional to v. Then modes in step index fiber. So here the important parameter connected with the cutoff condition is the normalized frequency. That means V number, or we can have V parameter. So V equal to 2 pi a by lambda whole square into Na square. So V parameter is a dimensionless number and that determines how many modes a fiber can support. So this is a diagram. So this one is gives the value of V, that is normalized frequency versus beta by k. So the plots of propagation constant as a function of V for a few lowest order mode. Now look at that, we have HE11 mode, TE01, TM01, HE21, HE12, HE32, like that we have many number of values according to the hybrid modes HE and TE modes. Then we have modes in step index fiber. So in the previous diagram, the plot of B, that is in terms of B by K as a function of V is one. So for a few number of lower order mode. So where the modes are cut off when beta by K equal to M2. So that means the HE11 mode has no cutoff and this is to exit only when the core diameter is 0. So by approximating the value, we can choose A, N1 and N2, that is the radius of the fiber, refractive index of the core and the refractive index of the cladding. So if V is less than or equal to 2.405, then we can say that it is the step index fiber. So where the value at which all the modes can accept modes can be exist except your HE11 mode. So thank you all. Thank you for watching this video. Thank you.